Alright, so let's take a look at using images in processing. In processing we have this useful class called pimage, or processing image, which we can use to load image into processing, and we use the image method to display these images. So let me show you an example of how that works in processing. We have a nice sketch here. Again, just to remind you, all these example videos, all these example sketches are on UTS Online, so you don't have to try and copy them from the video. But here we have a nice little simple sketch, which as you can see in the setup method here, well, actually before the setup method, we first of all create a variable of type pimage. So this is a variable that can hold processing images for us. And in the setup, we say that the picture variable points to an image that we load off disk. So when we use the load image method, that will look in processing's data folder for a file with this name, fall.jpg. And if we go to our processing folder, we'll see that there is the image. We then use this little bit of code to simply set the size of the processing window to be big enough to fit the picture in it. So we set the processing window to have the width of whatever of the picture that we just loaded in and the height of it. Then in the draw method, we use the image method here to display the image on the screen. So we pass in the name of the variable that has the picture in it that we want to display, and we tell it where to draw it. In this case, we're going to tell it to draw it beginning at 0, 0, the top left corner of the screen, so that we see the full image there. But we could, of course, draw it anywhere we feel like. So let's run that first of all, and we'll worry about this stuff in a sec. So there we go. We've shown that we can load an image from disk and display it in a processing window. Now you'll also see that we can do this sketch is a little bit more sophisticated. It's allowing us to, with the mouse, point at individual pixels, and up here it's displaying what the color of those pixels is, what the red, green and blue and alpha value is of those pixels. You should remember the alpha value is basically the transparency, or the opacity of the pixel, whether you can see through it or not. So as you can see, when I'm pointing up here, the blue value is quite high, and when I point down here at an area which is not sky, the blue value is quite low. So it's just giving you an indication of what the various colors are of all the pixels in this image. And the reason we're doing that, apart from the fact that it's just interesting and helps to reiterate what a bitmapped image is that we are showing you that in processing you can get the color of an individual pixel using the get method. So there's a get method here. If we pass in an x and y coordinate, it returns a variable of type color, which has within it the color of that individual pixel, which we can extract using code a bit like this. And we can extract that, and we can either display information about the color of that pixel, or we can do things in our code based on what that color is, or we could say transform the image by manipulating the colors of certain pixels to achieve some effect, and we'll do a bit more of that down the track. So that's the pimage class and the image method for displaying images, and also the get method for getting the color of individual pixels out. And I should point out that there is a complementary set method which allows us to actually set the color of an individual pixel. So again, if we want to change the color of a pixel, we can do that too. And if we do this, if we work with individual pixels, this gives us a lot of power and flexibility to manipulate our images. We can create well, all the kinds of effects that you would see in Photoshop, for example, are sort of using this basic technique of getting the color of individual pixels and manipulating them in some way. So pixelation effects, color changes, changing an image from being color to being black and white, adjusting the contrast or the brightness, all this kind of stuff you can do in processing too, and you can do it in real time, and you can do it in response to user actions. So let's show you a few kind of examples of how we might go about doing that. The first is a pixelation effect. So I'm just going to show you, this is the image that we're going to be working with in this example. It's the image that they use in the book, and it's a bit of a classic image that's used in a lot of research papers and things like that about computer imaging techniques. So that's the picture that we're using. If we take a look at our processing sketch, and work our way through it, we see again we're using the p image type. So we've created a variable of that type called image, img. In setup, we're loading the picture from disk into p image variable. We're setting the size of our window big enough so that we can see all of that image, and then we're using this no loop method, which essentially just tells processing to not call the draw method 60 times a second, and we do that just because we're only displaying a still image once. There's no point in it continually invoking the draw method, but it would still work the same way even without that line of code. Then if we look in the draw method, we are defining some variables here: resolution, x increment, which is the width of the screen divided by the resolution, and y increment, which is the height divided by the resolution. And then we've got a couple of nested for loops here. But before we go into what they're doing, let's take a look at what the end result is, and then we'll work back from there. So when I run this, we're getting this pixelated effect. So let's just open up our... Here is the original image. Here is the pixelated image. And what pixelation effectively is just taking the color, instead the color of we're taking the color of pixels at certain intervals. So in this case, I think it's every 50th pixel we're taking the color of that. So on the original image, we take the color of the first pixel, and we draw a big block with that color. Then we skip 49 pixels, and then we take the 50th pixel color, and we make the next block the same color as that on our target image. Then we skip another 50 pixels and get the value of the pixel number 100, and that becomes the color of the next block in our target image, and so on. We work our way through. Every 50 pixels, we take the color of that pixel and set the block to be that color in our target image. So we end up with a final image over here, which resembles the original image, but at a much lower resolution. So with bigger pixels and a smaller number of pixels. So that is what this sketch is doing. So let's take a look at how it does it. It has these variables. We have the resolution is 50. That's how many pixels we are skipping between the sampling of the original image and how we recreated it in the target image. The increment, actually this is slightly more complicated. The increment is the number of pixels that we're skipping between the samples from the target image that we're taking. Resolution is a number that describes that. And then here we have a couple of for loops. So basically we're working our way through each row. So for every row in the image, within that row we have a number of columns. Well, within each row we have a number of individual pixels. So we're working through each individual pixel in each row. We're setting the fill color in processing to be the value of the color of the pixel at X and Y. So initially X and Y are going to be 0. So we're going to get the color of the pixel at 0, 0. We're going to set the fill color of whatever we draw to be that. And then we're going to draw a rectangle with the size of the number of oh dear, this is confusing. Let me go back here. I've confused. I would no doubt have confused you, as I've probably confused myself. Resolution is not the number of pixels that we're skipping. Resolution is how many times we are dividing the width and height of the image by. So we're breaking up the width of the image into chunks, into 50 different chunks. To figure out what the width and height of each of those chunks is, we're dividing the width of the image by the number of chunks. So if we're dividing our image up into 50 chunks, the width in pixels of each little chunk is the width of the image divided by that number of chunks. And the height likewise. So the resolution is 50, so we're dividing up the width into chunks, into 50 chunks, and the height into 50 chunks. So for each row, we're starting at y equals 0 for the first row of pixels. We're checking to make sure that we're less than the height of the image, so we don't go beyond the height of the image. And then we're incrementing y by that chunk size. And we're doing the same for x. So we're starting x equals 0, we're not going anything beyond the width of the image, and then we're incrementing x by the chunk size that we're sampling. We set the fill color to be the color of the pixel that we're currently at, as I mentioned before. So initially 0, 0, and then we're drawing a rectangle which is the appropriate size, which is the size of the chunk that we're getting, the size of the chunks that we're sort of dividing the image up into. And then we go back and get the increment x. So the next increment x will be x plus whatever the width of the image divided by 50 is. So we're incrementing x by that number of pixels, and we're getting the color of the pixel at that value of x and y being 0 again. And then we're drawing another rectangle with that color, and we're continuing around and sampling our image 50 times across the width of the image and 50 times across the height of the image, and that's giving us that pixelation effect. I think maybe I've made it sound more complicated than it really is. Take a look at the code, and I think you'll get the gist of what's going on. The main point, I guess, of the exercise is not so much that you understand exactly how to write a pixelation algorithm, but that you can get the concept that we're using these get and set methods to get the color of a source image, apply some algorithm to it, mess with it somehow, and then set the color of a target image based on that in some way. I don't know if it's worth spending a lot of time on, but there's another example in the on UTS Online, which just does the same thing. It does pixelation, but in this, but what we do is get the mouse input so that we can dynamically change the degree of pixelation. So we can move from very small chunks, very low resolution, up to higher and higher resolution as we move the mouse around. I don't really want to go into that. It's pretty obvious what's going on. We just get access to the mouse X method, and we use that to set the resolution. You can take a look at that in your own time. I don't think it's too complicated. all worth spending a lot of time on here. And we can use other kinds of algorithms as well. So rather than pixelation, this sketch is creating an image that's like a photographic negative of a source image. So let's take a look at what's going on here. We're loading in this principal image, an image of a church somewhere in Europe, I'm guessing, from the look of it. So this is our source image. We're loading this into processing. And we're doing what we've done before. We're loading it in. We're setting the size of the screen so we can fit it in. And then in Draw, we're again going through each line and each individual pixel within each line. We're getting the color of the pixel. And then we're messing around with the color of that pixel. We're setting the color of the pixel in the target image to be 255 minus to have a color which has RGB value, where the R value is 255 minus the R value of the source image, the red value of the source image pixel. The green value in our color is 255 minus the original green value in the source image, and the blue value is 255 minus the color of the blue value in our source image. So in other words, if our source image has a pixel with a very high blue value and very low red and green values, our target image will then have the opposite of that. It will have high red and green values and low blue values. So we're basically creating what will appear to be a photographic negative of our source image. So let's run it and compare our source and target images side by side, and you can get a sense there of what's going on. So we're messing, again, not so important that you understand the algorithm, but you should be able to understand, I guess, why we're seeing an image of this kind, and you should also be able to see how powerful the approach of getting a pixel value from a source image and messing with it and outputting it into a target image can be. You can achieve a wide range of different effects with this. So, and also, I guess you should be noticing that with pretty simple kind of algorithm, really one line of code there, we're having quite a major impact on that image. Okay, final example. This is something a bit more dynamic. We have a sketch which is called Random Neighbor. Slightly more complicated, but not that much more complicated. So we are working with this target image that we had before, picture of a nice garden in autumn somewhere. We're using the same code as before to load that image in and set the size of our window. In Draw, we're drawing the image on the screen, and then each time the draw method is called, so every single time we're drawing a frame, we're working our way through, again, each line of the image and all the pixels, each individual pixel within each line of the image. And we're saying here that we're creating a variable called new x, and that is the value of rand int between x minus 1 and x plus 1. So x, remember, is the value of the current x pixel. Sorry, the current x coordinate of the current. The x here is the x coordinate of the current pixel. And what this method down here, random int, is doing is giving us a random number between x minus 1 and x plus 1. So our new x coordinate is going to be somewhere between the current x coordinate -1 and the current x coordinate +1. And exactly the same thing is going to be applying to our y coordinate. We're going to have a new y coordinate, which is a random number between y -1 and y +1. And then, using the set method, we're going to set the color of the current pixel with x and y. We're going to set the color of the current pixel to be the color that is at the coordinate new x and new y. So if you think about this, you might have to pause the video and kind of nut this out. If you think about it, what we're doing is getting the value of one of the pixels of our current pixel's neighbors or itself. So if you think about a pixel being on screen, there are sort of 3 pixels that are immediately above it. There's 2 pixels to either side of it, and there's 3 pixels immediately below it. They're kind of the surrounding pixels around our current pixel. So there is 8 neighbors of our pixel. So what this algorithm is doing is picking one of those 8 neighbors or the current pixel. It could also be the current pixel, and it is setting the color of the current pixel to be either the same as the current pixel value or one of its neighbors' values. So we're introducing some randomness here. We're saying, but not complete randomness. Again, to repeat, we're just saying the value of the current pixel is basically the value of the current pixel or one of its neighbors. And we're doing that not just once, but we're doing it every time the draw method is called. So just so we can see what's going on, I'm going to make the frame rate 2 frames per second so it doesn't happen too quick. And let's run this. So you can see now our source image is still recognizable, but gradually over time, each time we draw a new frame, the image is kind of devolving. So the colors are kind of, like the yellow color of the tree up here is kind of remaining in the same kind of zone it was in, but it's gradually transmogrifying. It's gradually moving around as we change the color of each pixel to be either itself to be one of its neighbor colors or its same color as it currently is. And if we change the frame rate to be, well, if we just take that line of code out, so the frame rate is 60 frames a second, we can see this happen a lot more quickly. And if I was to leave this running for quite a long time, you would sort of eventually, I guess, see the image devolve more and more, become less and less recognizable as we add more randomness in the image. But so it's randomness there, but it's kind of a constrained randomness based on the original image. So there are some examples of how we can use the get and set method in processing to access the color of the pixels in a source image, and how we can use the set method to sort of mess with those colors. And hopefully you can see that even through some of the simple examples I've given here, there's some quite powerful effects that you can get happening in real time in processing and potentially in response to user actions as well.